All right. All right, so somebody should be able to tell me what these functional groups are, or what functional groups are present. So in this first molecule, can somebody tell me what functional groups are present?
Ketone.
Yep, and that would be the only one. What about this one?
Alcohol.
Alcohol.
This one?
Aldehyde.
Yeah.
All right, and this one. Let me open it up a little bit. All right, so starting from the left, can anybody take a shot at it?
Carboxylic acid.
Yep. So it's basically your carbonyl group. So your ketone, but instead of carbon or hydrogen, it's an alcohol. What about here? In the previous semesters, this has confused a few people. What about this?
Amine?
All right, so remember our amide. We have our amines, but our amide are, instead of a carbon or hydrogen here, this is where our nitrogen would be. So this is our amide. Man, somebody left already. All right, so yes, this here would be our amide, not this, all right, because this is a whole bond separate from the carbonyl group. So what is in red wouldn't be our amide. Here in blue is our amide, and this here is our amine. All right, what about this big benzene ring? Is this a benzyl or a phenyl?
Benzyl.
Yeah. So what I just like to know that coming off of the main chain, there's just this extra carbon or this extra bend that it makes. So that extra bend, there's a benzene. It's a benzene. If that extra carbon wasn't there and it was just directly to the benzene ring, then it would be a phenyl. All right. What about last? Me is just methyl.
Ester.
Yeah.
Yeah. All right, so you guys are pretty solid on that. All right, so alcohol classification. Can somebody tell me? So when we're talking about alcohol classification, it's really primary, secondary, or tertiary. So can somebody tell me what classification this one would be?
Tertiary.
What was that?
Tertiary.
Yeah. So coming from the carbon that the alcohol is attached to, we have 1, 2, 3 carbons, which makes it tertiary. Wouldn't the OMe make it an ether? So Ashley, an ether is this, which I get your rationale, but you have your carbonyl coming off of that, which makes not just your, so it's kind of like an amide, but instead of the nitrogen, it's an oxygen. Does that answer your question? If this carbonyl wasn't here, and it was just this chain in OMe, then yes, it would have been an ether. Does that answer your question, Ashley? Just yes or no in the chat. Anyways, the next one. Can somebody tell me what classification this one would be?
Primary.
Yeah. So again, coming off of the carbon that the alcohol is attached to is only from here is one carbon. And last but not least, yeah, in case anybody's not looking at the chat, Erta, my partner, just if you just joined or joined late, just type your name in the chat.
Secondary.
Be secondary.
Yeah, it would be. So somebody said primary, so I'm just gonna, I don't know if they were talking about the second one, but from the alcohol, all right, so we're looking at this carbon. How many carbons is that attached to? Two others. So secondary. So it seems like you guys are pretty solid on that. Nitrogens. All right. Somebody tell me what classification that one is. All right, those that are typing it would be correct. So unlike the alcohols, which you're looking at the carbon that the oxygen is attached to, you're looking at direct attachments from the nitrogen. So the only carbon direct attachment would be this one, in which there's only one, so it's primary. What about this second one?
Secondary.
Yep. And there's our two carbons. In the third one?
Tertiary.
All right. So it seems like you guys are all going to get those ones right. Moving along. All right, so hydrophobic and hydrophilic. So when we're talking about hydrophilicity or phobic, it's usually in relation to water. So, like in chapter 3, you'll often see it in aqueous solution. And so we know that water is polar, and like Tito and Hochul used to say, like dissolves like. And so polar in something polar, it'll dissolve pretty easily. All right. So in vitamin A, can somebody tell me where the hydrophilic portion would be?
At the OH.
Why?
Because that oxygen and the hydrogen will bind onto more of like the water molecules, and plus that chain I kind of associate similar with like phospholipid bilayers, so I know that chain right there that is going to be hydrophobic.
Yeah. So as she stated, the right side of the molecule will be the hydrophilic portion because this alcohol is creating this dipole, and therefore it's making that side of the molecule polar. And so that side of the molecule, because it's polar, will dissolve in water because water is polar. And so intuitively, this hydrocarbon portion would be the hydrophobic. So it would not dissolve in water. It would repel from water because water is polar, but this side is non-polar. Does that make sense? And if so, how about vitamin B? Can somebody tell me where? All right. So Brenda, yeah. So It's just simply asking you, it's giving you a molecule and it's asking you which parts of the molecule will interact or dissolve in water. So water is polar, and so things that will dissolve in a polar molecule, like water, needs to be polar. And so that's what the red indicates. So this alcohol is making this side of the molecule more polar than the rest. And so this side of the molecule is what has a higher solubility in water. And of course, diethyl ether or ether is not polar, and so it would just be vice versa if you're doing it for that. Anyways, vitamin B, can somebody tell me which portion of the molecule has a higher solubility in water?
Would it still be the right side?
Yeah, why?
Again, the alcohol, it makes it very easy to be soluble.
Yeah.
Compared to the ring.
Yeah, and so this, not only the alcohol, but the carboxylic acid in general, you'll see later on that this is one of the highest priority that you're going to get. You'll see that in chapter 4, but also one of the more reactive species that you'll see in organic chemistry. Because it is so polar, it has all these electrons that it can use and this and that. But anyways, the carboxylic acid here and or alcohol is the polar portion. And so this portion of the molecule will be what makes it highly soluble in water. And as your classmate said, the rest of it would be your hydrophobic, because it's really just a carbon ring, and this nitrogen isn't really that electro negative. So this portion of the molecule will be your nonpolar and therefore hydrophobic in water. And again, vice versa if you're in a nonpolar solution. All right, boiling points. So, Urta, is there one you want to touch on?
I just want to tell you guys to keep in mind that everything, whenever they say soluble in water, keep in mind hydrogen bonding is very important. So everything you see that has a hydrogen bond, usually that part of the molecule is going to be the one that is going to be the polar side, while long chains of carbons are usually nonpolar. While that nitrogen right there so that nitrogen is electronegative, and you only form hydrogen bonds with N, O, and F, right? And nitrogen is one of them. Ideally, the ring makes it very hard to go and form a bond there. So, like, generally, that structure on the second structure, right? The ring structure is going to be sort of nonpolar, even though it has that nitrogen right there.
All right. So yeah, as you stated, if there's something that has a bit of hydrogen bonding, then yes, it will again be soluble in water. And I just got a message from Tatiana. I don't know what it is, but is Tatiana here? Okay. All right, so boiling points. I'm just going to ask which one of these will have the higher boiling point?
The alcohol.
Why?
Because of the hydrogen bonding being stronger than that dipole-dipole force. So it's going to need more energy to break apart the hydrogen bonding.
Yeah. So Raya, you're also correct. This does have more surface area, in which would increase the boiling point. But primarily, one of the easiest things you can do is look to see for which one has hydrogen bonding or which one has more hydrogen bonding. So just asking which one has the higher boiling point would be this one here. How about the ones with the fluorine?
The trans.
Why?
Because when you have it like more compact, it's gonna melt slower, but it'll boil faster than with the cis side, because that cis side, it'll melt faster, but it's gonna take a longer time to boil because it's less compact.
So
and it's able to
one
kind of fit.
Yeah, that is a very good rationale. But one thing I would like to point out is dipoles. So which one has more of a dipole, and how would that influence the boiling point? So if you have more of a dipole, would that increase or decrease the boiling point?
In comparison to the trans one, the cis one has more of a dipole moment.
And so would that increase or decrease the boiling point?
Increase the boiling point. You
So-
need a higher.
There you go. So, okay, now it's going to act up. All right, I think I'm just going to have to share my screen.
Yeah, Word does that a lot. Raya, to answer your question, technically speaking, the first molecule that we talked about, both of those, the carbonyl and the alcohol, both of those have, how many? 5 carbons there, right? Yeah, so 5 carbons. So both of those have 5 carbons. So technically, lengthwise, they're going to be the same lengthwise, right? But you could argue that there's more surface area for the carbons to interact with each other with London dispersion forces, but that's not the main thing that we're looking at for that one. It's easier to go through hydrogen bonding than to go through London dispersion forces. But you are right, technically they are the same length because they have the same amount of carbons in the molecule.
It's a good way to look at it. Somebody messaged me, Sabrina Hara or Jara. If you guys have a group chat, go ahead and tell her to again use the link that I posted in the discussion tab instead of the Cisco.
She's here.
Okay. Anyways, so yes, this one will have a higher boiling point because of the increase in dipole. The dipole in this one simply just cancels out. So the more of a dipole that you have, the more, the higher the boiling point there would be. How about this one?
The second one.
And like Eartha said, the one easy way of looking at it is there's this one has another hydrogen bond in comparison to the first one. So again, more hydrogen bonding, there's going to be a higher boiling point. And lastly, since the same person is answering, how about George?
The first one,
Why?
the hydrogen bonding.
Yeah. Yep. And because this group is at the end, there's also an increase in dipole towards the end of the molecule in comparison to the other one. So not only is there hydrogen bonding, there's also a higher dipole. But yes, this molecule will have the higher boiling point. All right, IR. A lot of people stress over this when really he's not going to ask any more than like 4 questions on it. And you'll never see it again, even in the final, maybe. But this one, this is what I've always shared. This is what Brenda asked if it's in Orgo 2. Yes, your first test in Organic 2 is all Chapter 9, which is NMR. And you're in Orgo 2, you're really just going to see it in Orgo Lab. Because Dr. West really likes NMR. It's kind of what he does for a living, actually. But I just wanted to highlight some of the main groups that you want to focus on, in which are the more noticeable groups, which would be this C double bond O. Oh, okay. Big bitch. Let's see. All right, so your C double bond O, if you have a carbonyl present in the molecule, it will show up in this range here, and it will be a long and sharp peak. And I think I have an example. So yes, here's a carboxylic acid. If on the bottom right of this graph, there's a carboxylic acid, and of course the portion of a carboxylic acid is the carbonyl, in which, similar to just this diagram, you have your C double bond O stretch. It's very noticeable. Let's see if I can draw on it. So here is your C double bond O, and again, IR, it doesn't tell you the structure, it tells you what is present. Keep that in mind because you might just throw out a conceptual question. Moving along, the one that, I'd be pissed if somebody got this one wrong, but an OH. Your OH stretch is always going to be higher than 3,000 centimeters, and it's going to be something wide and broad. All right, so this is what you see here. Again, here's this carboxylic acid that's present. A portion of the carboxylic acid is the alcohol, in which you see this big, broad peak is indicative of your alcohol. All right. Is there really another one? Because
the amine.
Yeah, your nitrogens kind of, they can blend in sometimes. Do I have? I don't really have an example, but the most common way you're gonna see in an amine, it's almost like teeth, little teeth. All right, so it's not going to be as prominent as your alcohol. You know what? Let me just see if I can pull up an example for you guys. I'm sure you guys have already seen it, but. Yeah, so like I was saying before, your amine, especially if it has, it's not a complex amine. If it's just a simple amine, you're gonna see this smaller, like a tooth-like peak above 3,000, which is indicative of an amine. Let me see another one again here. Let me see. So yeah, here again, it kind of looks like teeth. Again, above the amine, above 3,000, and a peak that looks like this is indicative of the presence of an amine. And so, yeah, those are the main three that I would keep in mind. Other ones like this big thing, that's not an alcohol, that's actually just a bunch of CHs. And again, here, your amine stretch is blending in to your CHs. And so a lot of people kind of get confused on that. Here's just a bunch of CHs in a molecule. But again, above 3,000 kind of looks like a tooth, like a canine tooth or two teeth. A vampire is indicative of a amine. So again, those are the three ones that I would definitely keep in mind: is your amine, your C double bond O, and your alcohol.
Yeah, so I just want to add something. So as Michael said, keep these three in mind is very important. And keep in mind that IR only shows you functional groups. Now, when you do your assignment, your discussion assignment, you might see some different groups. Sometimes they do C triple bond H, C triple bond C, or something like that. Don't freak out. Just pull up a table. You have a table on your book as well, or you can pull up a table online and you can look up those IR stretches and values. So don't freak out. Usually in your lecture, you're only going to see those three groups. But for other stuff, you might have to work the system a little bit.
All right. And yeah, like she stated, so here was the former bonding question. So can somebody tell me, or go ahead and just, can somebody tell me what peaks they would expect to see? Just A, B, C, or D.
B.
Does anybody concur?
I mean, I'm not sure, but isn't it like a OH, and that is like strong and broad from the region 32 to 3400? So I would be, I don't know, with D probably. I'm not sure.
Yeah, I think D too.
I feel like B and C are really, really similar because they're supposed to the double bond peak, right? So that double bond region, isn't that near 1650 as well as near as 1710?
Yeah, because D says only a peak, so it has to be B, right?
Yeah, so you guys are definitely thinking about it the right way, and luckily for bonding, you guys can eliminate one of your submissions and still get full points. And so just process of elimination, you guys have already canceled out A and D because in an IR, it's going to detect both of these groups, the double bond and the OH. And fortunately, germane isn't going to test on something this close. I don't even know why this showed up in bonding. It's almost way too close to even say. And on an exam, really either of these would be correct. But I think when I took this class, it just, for some reason, it said that C was the right answer. But again, I don't know the rationale for the system. And for some reason, I don't get why it gave me those two those two options, but on the exam, he's not going to give you something this close. So as long as you guys thought about it correctly, and if you apply that, you guys will get something like this correct. I think. Do I have another one? All right, yeah. So this one. So you're going from one molecule, say you react it, and you end up with a product. So could somebody tell me what would appear and disappear?
Off rip, you would get the appearance of that alcohol group showing up around the 3300.
Yeah. So we can, obviously there is a functional group that is changing. So D is not going to be right. And B doesn't even indicate that there is a alcohol in this reaction when really there is. And so B isn't an option. Bitch, this is B.
I think it's A. Because the double bond disappears. So the peak at 1710 would disappear.
And that would be correct. So we eliminated B and D. She said that she sees a C double bond O and knows that is something around this. So therefore she concluded A, which would be correct. Any questions on that? Right. So
I have a quick question, actually.
Yeah.
So the chart that he's going to provide, it has these, like what's necessarily on it, because I'm just going off of a chart that I drew myself. But is there the measurements and is there the regions stating where, or is it just the measurements?
So one that is very similar is it's gonna give you the group and the range of in where you would expect to see it. So it's definitely not going to show you the shape. That's why I made sure to show you guys this. This is really, really simple. A simple diagram that shows you the main ones. But one that would be similar to something you would see on the exam is something like this. And so it would, I don't remember if it told you the strength of it, and the strength just indicates how far down the peak is, but it'll give you the name of the group and where you would expect to see a peak.
Yeah, so you wouldn't actually see a graph with the peaks. You would just have that. And that's why we told you guys to remember kind of the strengths and everything and how they actually look like.
Yeah. So does that answer your question? I don't know who spoke.
Yeah.
All right. So we did that one. All right. So for a quiz question, you guys already took a quiz. So could somebody tell me, so it's asking for which solvent is best for dissolving this salt?
Would it be B?
Why?
Because it's more polar.
Yeah. So you guys know from chapter 3 that these potassium ions are just going to float away, and so you end up this CO3 looks something like this. So if you were to draw the Lewis structure, you'd get this, and you see that this is polar. It's definitely not that. That's as non-polar as it can get. And so A is more polar than C, but it's not as polar as B. So yes, B would be correct. And yeah, Urta mentioned it. I'll post the document that I'm using in files after the session. All right. So which one has a dipole of 0D? And again, D is just nomenclature. It's just a symbol for a dipole.
B.
Yeah. So it seems like everybody's, agrees with that. If you were to draw these out, you'd kind of see that all the other ones they have a net. I'm not going to draw all these out, but if you were to draw the Lewis structures of them, not even Lewis structure, but like a bond line, like this ethyl, you'd see that there's a net dipole upwards. And if you were to draw it out among the others, you would see that as well. And so something that has a net dipole of 0 is something where the dipoles all cancel out. All right, somebody mentioned melting point. So can somebody tell me which one of these has the highest melting point?
B.
Does anybody disagree? Agree? All right, so people are confused. So the answer would be C. I get the rationale for B because you have this alcohol and this ring is compact. But so when you're looking at melting point, you're really looking at the shape of something. So just to give you a life example, if you were to stack softballs or baseballs onto each other on the floor, it's simply not going to work, right? Because they're not compact. They're not able to stack on top of each other. If you were to stack books on the floor, that would be easy as shit. They can all stack on top of each other. They all have a similar shape. And so again, things that can be compact will have a higher melting point. Because again, instead of vaporizing something, you're simply taking it from a solid to a liquid. And this 3D, the key between this B and C is this 3D structure. Because something that's 3D, like a sphere, this is more sphere-like, and so it's not going to if you had a bunch of these molecules, they aren't going to compact like these two examples here. So to break down more of the rationale, so melting point, if you want a higher melting point, all right, you want it to be more compact. All right, you want it to be more sphere-like, so more 3D. More branching. As you can see, there's this has 4 groups branching off of that carbon, so more branching. And stronger intermolecular forces. Similarly, but some differences. If you were to if you want a higher boiling point, then again, something that we spoke of before, you have more hydrogen bonding, less sphere-like, so less 3D. Less branching, and more surface area. So these are, is increased.
So based on what Michael just wrote, what do you guys think? Which one of those would have the highest boiling point? A, B, or C?
B.
Yeah. So A is a good guess because it's less compact, as we would say, but keep in mind hydrogen bonding on B makes the boiling point higher because it takes more energy to break a hydrogen bond.
Yeah, so if you were to look at these points that I made, I'm just going to erase this. So you can see it all. So the difference between A and B is that these are both rings, and so they're not 3D. They both can be flat and lay on top of each other, just like books, like I said before. They're both relatively compact, but you have this alcohol, and therefore you have more hydrogen bonding. So that just adds an extra oomph to make it a higher boiling point. And so go ahead and take note of that. Those are what you want to know. That's really all I have for you today. Jermaine sent us something, but Ertz and I kind of agreed that it was pretty pointless. SA, surface area.
Yes.
So yeah, Lancy, I'll post this document that I used onto files. So yeah, just like before, I'll send out a recording, and so like with the handout, you guys can go through it with it as well. What should we really focus on for the exam? So something that that I know you're going to get less of. The least thing that you're going to be asked about is IR. You might get like 3 or 4 questions on that, no more than a handful. Chapter 3 is definitely high yield because it will. That's kind of the intro to reactions that you're going to see in chapter 6. So he's probably going to love. He's going to love chapter 3.
Be familiar with resonance and stuff. Constitutional isomer, resonance, same molecule. He asks a lot of that as well.
Yeah, arrow pushing. You guys will definitely be tested heavily on arrows. So guys, keep in mind, like we were saying before, arrows simply indicate the flow of electron in the direction of where they're going. So a very easy question that he could come up with is he gives you a reaction, say acid and base, he gives you a reaction, and he gives you your 4 choices. And among the 4 choices are the arrow pushing, and one of them is simply, and you guys should be able to recognize the correct direction of where the arrows and electrons are going to go. So that's something I've seen several times in my exam and others. So yes. So mainly chapter 2 and 3. I wouldn't say mainly. I think there's going to be an even split between 1, 2, and 3, just excluding IR. IR again he's not going to ask more than like 3 or 4 questions on it. The primary thing that he's going to ask you guys about for chapter 2 is the 10 functional groups. So you can just flashcard those. And again, just your boiling point will be a common one. Guaranteed, you're going to see that a few times. Another thing you guys should practice is isomers. So getting the constitutional isomers or recognizing which ones wouldn't be or would be the constitutional isomer. Erta, is there anything you want to add to that?
Not really, yeah. I think that should be it.